Hi, in this example we will discuss fixed point math, which is a way for the 9s12 to deal with non-integer values. The precision of a number determines the range or the number of alternatives it can take on. In this example we will see both 8-bit and 16-bit precision. And lastly, we will consider dropout, which occurs on a right shift or a divide, or overflow, which can occur on a multiplication or an addition. Let's begin. In this example, we are asked to take an 8-bit variable n, add 5.5 to it, and then multiply that sum by the number 2.3. We can visualize this graphically by looking at the relationship between n, which is the input, and m, which is the output. As n goes from 0 to 255, m goes from 12 to 599. This linear scaling is a way to convert one number system into another, just like we would be converting, say, Fahrenheit into centigrade. All right, where do we begin? We can't store the number 2.3 or 5.5 in the 9s12, so we need a way to convert these non-integer values into an equivalent integer expression. For example, if I take the 2.3, multiply it times 10, and then divide the whole thing by 10, the 2.3 is converted to an integer. So, we have a 23 times an expression divided by 10, which is the equivalent of multiplying times 2.3. Continuing along in this way, if we multiply the top by 10 again, and the bottom by 10, the 5.5 is converted to a 55. And now this expression is equivalent to the original expression, but it contains only integer values. 10 times n plus 55, that quantity multiplied times 23, and then that whole thing divided by 100, is equivalent to the operation that we were asked to perform. And this is an example of fixed point, which is a way to convert non-integer calculations into equivalent integer calculations, which will be much easier to perform on the 9s12. Before we solve it, we'll simplify it one more time and distribute this multiply into the expression, giving us a little bit simpler calculation. 230 times n plus 1265, then divide by 100 and store it into m. That is what we will implement. In summary, fixed point is a way to represent non-integer values by the quotient of two integers. 2.3 will be performed or represented in this software by 230 divided by 100. But there are more than one answer to this problem. For example, we could have divided by 1,000, giving us 2,300 times n plus 12,650. That divided by 1,000 could have been used. But notice that the intermediate results here are going to be 10 times bigger. And therefore, this intermediate result is 10 times more likely to overflow than the previous one. And so we see that as the denominator of this choice gets larger, the possibility of overflow in an intermediate result increases. On the other hand, if we had chosen a smaller denominator, the numbers would have been smaller, and the likelihood of overflow in an intermediate result would have been less. However, you can see that the 12.65 is now approximated by 12.7. And so we see the smaller we make the denominator, the more dropout, or the more error in the lower bits will occur. So far, we've been considering denominators which are powers of 10, 1, 10, 100, 1,000. But it doesn't have to be that way. Fixed point can allow us to choose any two integers to represent the non-integer value. For example, the 12.65 could have equally been represented as a 253 divided by 20. Similarly, the 2.3 could have been represented by a 46 divided by 20. So the point is, as we implement fixed point calculations, we are free to choose both the numerator and the denominator. So in summary, as the denominator gets larger, the error will go down, but the possibility for overflow will go up. we do have the opportunity to choose both the numerator and the denominator in our representation of that fixed point value. This allows us to accurately represent many non-integer values using small denominators, minimizing the possibility for overflow during an intermediate calculation. We saw many approaches. The one we'll implement in this solution is to multiply n times 230, add 1265, and then divide by 100. This is the way we would have solved it in C. This solution will first require a multiply. We're going to use the MUL or mul instruction, which takes register A, multiplies it times register B, and stores the result in the 16-bit register D. Both the inputs and outputs will be unsigned in this example. So, to set it up, we'll bring n into register A and the constant 230 into register B. When thinking about overflow, we'll consider the values that might be in the registers during the execution. After the load A instruction, register A could be any value from 0 to 255. Then, after the mul instruction is executed, register D will have the value 230 times n. Since n could be 0 to 255, register D can now be anywhere from 0 to 58,650. Luckily for us, 58,000 is less than 65,000, so no overflow has occurred. Next, we'll add the constant 1265. Now, register D contains the value 230 times n plus 1265. More specifically, register D can take on the values of 1265 to 59,915. Again, no overflow can occur in this addition because this will always fit into a 16-bit number. We're going to use the IDIV instruction to perform the division. So first we need to set it up. We're going to use the IDIV instruction to perform the division. Register D already contains the appropriate dividend, which is 230 times n plus 1265. But we will load into register X the divisor, or 100, by executing the load X 100 instruction. Pound means immediate. After the IDIV instruction, X will have the quotient, or 230 times n plus 1265 divided by 100. By the way, register D will get the remainder of this division. When we consider overflow, we'll take the range of values on the input, divide them by 100, and see that the range of the output will be from 12 to 599. Notice this range of outputs is exactly the specification of the problem. In other words, M should go from 12 to 599. And the last step is to store this result, which is here in register X, and stored into the memory location M. And we're done. In summary, we saw that we implemented a fixed point operation by essentially converting the non-integer value into a quotient between two integers, remembering to multiply first and divide second. We also looked at 8-bit numbers in registers A and B versus 16-bit numbers as we saw them in registers D and X. When we divide, we have the possibility of dropout, which is a loss of the lower significant bits. So to minimize dropout, we did two things. First, we multiplied before we divided. This significantly reduces the amount of dropout. The second thing we did is when we designed the fixed point algorithm, we chose a denominator that was large enough so that this fraction, for example 230 divided by 100, accurately represented the constant 2.3. Overflow can occur after a multiply or an add. We eliminated the overflow error in this example by using a precision large enough to contain the entire number. In this case, the number would fit into a 16-bit register, and therefore in this case no overflow occurred. Thank you very much.